let's find the local extrema for this function. F of xy equals 2y cubed plus x squared y plus x squared plus 5y squared. So we start off by taking the partials. The partial of f with respect to x, what is that going to be? Well, okay, this guy is a constant with respect to x, so the derivative of this guy is 0. This guy will become 2xy, using the power rule, and thinking of x squared as what we're taking the derivative of. Y is just a constant, plus 2x. And then likewise, this guy goes to 0 when you take its derivative. And then the partial of f with respect to y becomes 6y squared when we take the derivative of the first term. Second term, just x squared y. Just x squared. The third term goes to 0. X squared is a constant with respect to y. And then the fourth term would become, by the power rule, just 10y. And then we'll remember what we do. Critical values occur where the partials are either undefined, which won't be a problem with a polynomial function, or where they're equal to 0. So we'll set both partials equal to 0 and solve this resulting system of two equations, two unknowns. It's not as bad as it looks. Let's take equation number 1. So taking equation number 1, we know that 2xy plus 2x equals 0. Let's solve this by factoring. So I can factor out a 2x. So I'm going to go to the right. The arrow, this arrow means implies. So this equation implies let me say it this way. 2x y plus 2x equals 0 implies that, okay, if we factor out the 2x, then this equation will be equally true. 2x times the quantity y plus 1 equals 0. So this equation implies this equation. This equation true implies this equation true. It's another way to think of it. So the arrow, again, stands for the word implies. Okay, and then what? Well, I can set both factors equal to 0 and get either x equals 0 or y plus 1 equals 0, which implies y equals -1. So let's take a look. These are basically two cases. Let's take a look at both cases. If x equals 0, then by equation 2, 6y squared plus x squared, but x squared is 0, so this whole thing goes to 0, plus 10y is equal to 0. And okay, that equation implies that, okay, if you factor out 2y times the quantity 3y plus 5 equals 0. Which means either y equals 0 or y is equal to -5/3. So we actually have two critical points corresponding to when x equals 0, this first case here. The critical points are, so the CPs are 0, 0, and 0, negative. I should have written 5/3 there. Because remember, I solved this, set that equal to 0, solve, you get -5/3. So we get 0, 0, or 0, -5/3. Okay, just keep these two critical points in mind. Just save these for later. Okay, we haven't looked at the case. We looked at the case when x equals 0. Let's look at the case when y equals -1. So if y equals -1, then by 2, equation 2 up here, I think you can see it. Okay, we'll plug in -1 for y, and what do we get? We get 6 plus x squared minus 10 equals 0. And that equation implies that x squared is equal to 4, or that x is equal to plus or minus 2. Take the square root of both sides, don't forget the plus or minus. Okay. So that gives us, what, 2 more critical points, doesn't it? The CPs are -2, -1, and +2, -1. So 2 more critical points. Now we're going to use the second derivative test to find the local extrema. In order to apply the second derivative test, we have to find this thing called d. If you want to write it in terms of x and y, you could use function notation. d of x, y, remember, is f sub x, x. In other words, the second partial of f with respect to x, times f sub y, y, minus f sub x, y, the whole thing squared. So we need to find this to apply the second derivative test. Okay, so how do we do that? Well, we've got to take the second derivative. So remember, f sub x is 2xy plus 2x. So what's its derivative? With respect to x, we're going to get 2y plus 2. So going back down here, using, again, kind of the shorthand notation, I'm leaving off the of x, y. I'm leaving this off on, I'll put it here, but I'm going to leave it off on most of them. So that would be 2y plus 2. If you go back up and take a look, the second derivative, the first 2 derivatives with respect to y, you'll get 12y plus 10. I'll show you. Yeah, okay. Take the derivative of this guy. With respect to y, you get 12y. This guy 0. This guy just 10, plus 10. Okay. And then, should have stayed up there, because f sub x, y we can get next. That turns out to just be 2x. If you think about it, take the derivative of this first guy. This is the derivative of f with respect to x. Take the derivative of that now with respect to just y, and you get just 2x, don't you? This guy goes to 0, this guy goes to 2x. Okay. So that d as a function, d of xy, is then this guy times this guy minus this guy squared. So that, I'm just going to write that down. 2y plus 2 as a quantity times the quantity 12y plus 10, and then minus, well, okay, if you square this guy, you'll get minus 4x squared. And then we're going to plug in our critical points, see what happens. So if we plug in 0, 0, the first critical point we got, then we'll just get 2 times 10, which is 20, right? Because when you plug in y equals 0, x equals 0, everything else zeroes out. We'll get 2 times y, which is 20, and that is greater than 0. So we're in business. When d, that quantity d, is greater than 0, the corresponding critical point will either be a local min or a local max. And depending on the sign of the second derivative with respect to x, when you put it in to, I should say when you insert the critical point, which in this case is 0, 0. So what's the sign of that? Well, okay. We'll say f sub x, x, then we can see it right up here. When you plug in 0 in here, you'll get, well, two, because this guy zeroes out as well, right? And that's greater than 0. And when the second derivative is greater than 0, then the critical point corresponds to a local min. So what is it exactly that's a minimum? Well, this implies then that f of 0, 0, which if you go back and look at the function, that's equal to 0. It implies that f of 0, 0, which equals 0, is a local minimum. So there's one answer. Now, the next critical value, remember, was 0, negative 5/3. So we're also going to plug that in to D. Now, if we plug that in, you're actually going to get 40/3. You can check me on that. So you're going to plug in, if you go back up and look at D, you're going to plug in 0 for x here, so you'll be subtracting off 0, and then negative 5/3 here and here, and you will get 40/3. You can check that, and that is greater than 0, so we are in business again. So what? So if you plug in this critical point into the second derivative with respect to x and look at the sign, that'll tell us whether we have a local min or local max there at that critical point. So f sub xx evaluated at 0, negative 5/3. Turns out that will be less than 0. You guys believe that? Again, if you go back and look at D, then what happens? So look at this version of D. So what happens when you plug in 0 for x? Okay, this guy is 0, right? And then when you plug in negative 5/3, this guy will be negative, and this guy will be negative, so you will get a positive. And it does turn out to be 40/3. If you want to check that either by hand or on your calculator, you can do that. So what? Well, that's less than 0, which means f of this critical value, 0, negative 5/3, actually corresponds to a local max. So that implies that f of 0, negative 5/3, which turns out to be, so go back to the original function, plug in 0 for x, negative 5/3 for y, and you will get 125/27. So this is a local max, and it occurs at this critical value. Or critical point. Let me say that again. The 125/27 is the local maximum of the original function, and it occurs at the critical point when you plug in 0, negative 5/3. Finally, when you take D of plus or minus 2, negative 1, you can do both critical points at the same time because you'll get the same value. You get something actually that's less than 0. And you can see that if you go back and look at D. If you plug in negative 1 for y, these guys, these first two factors, 0 out because this first factor will be 0 times the second factor makes 0, and you'll be subtracting off a positive number. It's got to be negative. And when that happens, you've got yourself a saddle point on that graph. So what does that mean? That implies that plus or minus 2, negative 1, when you plug in those values into the original function, you actually get a height value of 3. So that implies that plus or minus 2, negative 1, 3, both of those are saddle points. And that's it.